Good morning, everyone. Before we start, do you have any questions from yesterday? So if we go to the ARCHER2 training page, I will put that on the chat. And we go to the course that is GPU programming with kernels. You see that the third session is already on YouTube, so you can have a look. Actually, was uploaded yesterday, so you can have a look about all the things that we explained yesterday. Let's go to the course material. Also, regarding the course material, I did an update on the timetable to keep it like as accurate as possible. Just to yesterday, what we have a look was to the types of memory that we have on the GPU. We have the global memory. We have a shared memory, constant memory, and also we saw how rather than using explicit allocations of memory, we can use managed memory instead. What else I wanted to share? Before we start with the exercises, maybe because yesterday some people asked me about like additional material. Actually, this will be like a good. So if one moment. So I would recommend you as an additional material to have a look at this documentation of AMD ROCm software. As the title said, is introduction to the heap programming model. But here there are a lot of concepts that could also be similar to if you use CUDA. So I will make this a little bit, I'm not sure if this is like a big, yeah, we'll make this a bit bigger. So here I talk about the hardware differences between CPU and GPU. I will copy the link on the chat. And also talks about the heterogeneous programming. That is like a program. This is like the normally when you use accelerators or GPUs. This is the workflow. You initialize, you transfer the data from host to device, you execute the kernel, and then you copy the data back to from the device to host. Talk about the device programming, the execution model. Also, this is quite interesting, the hierarchy of like the thread model. We were talking yesterday that we have works that are a set of threads, and these works belong to a number of works belong to a block. And normally on our application, we have several blocks inside the grid. Here is explained in more detail what is a warp or a wavefront block. That could be 1D, 2D, 3D, and also the grid. Here is interesting, the memory model. We have you see that we were talking yesterday about the shared memory, and you see that the shared memory is shared between the threads that belongs to the same block. So we have here two blocks, and each block has a different shared memory. And also we have access to the global memory, and you see here that the constant memory is in this small part of the global memory. And here they talk about local or per thread memory. That is the compute units, the CUs, shared memory, and the global memory. Yesterday we talked about the constant memory. And here in this graph also we can see what we talk about the axes that must be a coalesces axis. So if we see here on the left hand side, we see that we have the axes are not coalesced. So you see that for instance the thread 0 access position 0 of memory, but there are like some crossing. And the problem here that when we retrieve data from memory, it will not be efficient. So the idea is to have what we have here on the right, that thread 0 access position 0, thread 63 access. So you see that the accesses are coalesces. So talk more about memory, the execution model. We will learn today about the streams, so you will understand what that means. Asynchronous execution and multi-GPU, that we will see that tomorrow. There is a similar guide if we go to CUDA. I will copy this link as well here in the chat. We have also the CUDA, the C++ programming guide, that this is like a, yeah, well, you see all of these sections that we have. Again, it talks about the architecture of the CPU and GPU, also about the memory. For instance, we were talking about heap is a warp or wavefront. Here is a thread. We'll talk about the thread block. So the ideas are the idea is similar. Maybe you could change the name, but well, this guide is like quite. They have also a lot of code, samples. So I would recommend you if you want additional material. Here, this is also a good. And just to finish, if we go to the ARCHER2 training page, if we go to past course material and you search AMD, this course is quite good, accelerating your applications with AMD GPUs. This was delivered by AMD, and this was in four afternoons. And you can see for each day the timetable, and you have the sessions are recorded. So I would I recommend you to have a look at this because yeah, it's they cover advanced OpenMP, heap, also talk about the MI300, more about the RockProf, Omnitrace. So I would recommend this course. Okay, so let's start with the exercises. Any questions so far while I switch windows? Okay, so I will make this a little bit bigger. Yeah. So we are here in section 04, and we will start solving the exercise. So the idea of the exercise, let's open it. So we have this operation here, and what we will do is replace heap malloc, heap element copy with manage memory. This will be the part 1, and the part 2 will be other prefetching, and see if that makes a difference. You see that this is already, well, we have already a kernel here. So what we will do is we will copy the make file from section 1. Oops. 201 make file, and we will do a make. And we will submit our job. Also, I would like to show you I did a modification here. Because I'm only using the time that the kernel lasts, so I'm just using rockprof stats. It doesn't generate traces, but generates it is good enough for the exercise that what we will see now. So what I will do is submit. So sbatch submit. Oops, that was fast. And if I see the slurm file, yeah, we see that the result is correct. And also we will see that the time that took was this one. I will make a copy on here on a file. Actually, I will copy that on the right. So let's start modifying the exercise. So the idea here is that to have it, because we are using manage memory, we will not have a pointer to host or a pointer to the device. We will have a unique pointer. So for instance, this one, I will edit the name, and we will have X, Y, and A. We will not need that. So I can comment here. When I allocate memory here, because I'm using to allocate memory, we will not use this. And also to initial, well, actually, okay, I will write here. I will copy this section here. Oops. So what I will do is I will do heap malloc manage. Heap malloc manage of x, y, and a. And here I will initialize x and y. I don't need that. Also, I don't need to do a mem copy. And here, yeah, I can use a heap and mem set, but remember that the pointer is a. That's it. When I call the kernel, remember that we have different names. Again, because we use managed memory, we will not need to copy the data back. I think that's it. Well, we don't need that. And yeah, heap, yeah, we will need to free the memory. Okay, I think all should be okay. I'll see if that works. I will compile the code with make. Ah, I knew it, that there are 3 errors. Ah, well, okay, well, in the, yeah, that makes sense when checking the, yeah, now should be okay. Let's see if that. And now if I submit with this batch, submit, we'll have a look. Yeah, it's finishing. And if I see let's learn 165, yeah, the result, yeah, correct. And if I print this, I get that my kernel is taking this time here. The performance. So you see here that yeah, using managed memory is not that is, let's say, it's easier to code, but it's not that efficient because the runtime needs to figure out when to make the copy, when from host to device or device to host. So the data transfers may not be the accurate. The second step here is to check the using prefetching and see if that makes a difference. We will see that in a moment. Give me a second. Got too many windows open. We'll close this. Actually, we can do the prefetching. If we go to the top of the they said that the add prefetch request for X and Y before the kernel and the matrix A after the kernel. Okay, let's do that. So here we will need to add the prefetching. That the prefetching is, let me check the documentation. Yeah, I'm just checking the section that is. I will copy that on the chat. Oops. Yeah, I copy the link, but I don't want the link. I want this. So I want to use heap assert. So the pointer that I want to send is X. The number of bytes will be this one. See if I can copy and paste. Where I am here. Oops. And the device, I have here the device. You said the device number. So I had to do this with X and Y. So now I will do the same with Y. Yeah, Y. Right. let me check one thing before. Right. Okay, so I will leave it like that. I will go like a step by step. And now if I do make, and now I execute, splash, submit, sh, we see if that makes a difference. This prefetching. Okay, this is finished. Yeah. Check. Well, result will be okay because we haven't modified anything, but we better to double check. If we print this, yeah, well, we got a similar. Prefetch. Yeah, I'm not sure if both the. Well, no, actually, okay, actually it's slightly faster. I'm pretty sure that is not the right spelling of. Yeah, exactly, it's prefetch. Sorry about that. Yeah. Let's check modifying, doing the prefetching for the matrix after the kernel execution. We can do it yeah, here. Oops. Yeah. And yeah, this must be enroll and call. Actually, here there is a mistake. Sorry. When we do prefetch, okay, this is important here. When we do prefetch from host to device, we need to specify the device, the number, the GPU number. That is, we got it here with the heap get device. But if we want to do the other way around, we will need to do this. We will need to use a heap CPU device ID to get the prefetching from the device to the host. This is on the section on the documentation. Let's do make. Let's submit. Patch submit. Running. Finishing. And done. Okay, so cat learn is 279. Yeah, the number of is correct. And cat result stats CSV. Let's see if that well, okay, so slightly better, but yeah, this is the, well, not this is like a, when you use managed memory, the advantage is yeah, is maybe faster to code and you don't need to bother about memory copies, but you see that the performance is not that good. I'm not sure if in newer versions of Rock M this is better, but normally it's like that when you use a managed memory, the performance is not that good that using explicit allocations on memory. Cool. So this is the exercise of managed memory. Any questions so far that you may have? If not, we can have a look at the exercise of on shared memory that, well, could be a little bit tricky, but it's not a big deal. Okay. I will, okay, this is the, a lot of windows open, it's getting a bit of a, I will close this. I will close this as well. Okay. Okay, so now we go to the terminal. Oops. And we go to section 2.05. Have a look at the exercise. So this is the use of shared memory and atomic updates. Right, but the exercise is not here. So I will share. I will show you the exercise. Okay, so we have this kernel here, this function, and we will do the vector scalar product of two vectors, x and y. So what we will do is we'll use a shared temporary variable to store the contribution from each different thread in a block, and then compute the sum from for the block, and then accumulate the sum from each block to the final answer. it's also possible to use atomic add, only atomic add, but we will see the performance implications on that. Okay, so I will share again the terminal. Sure. Yeah. Okay, this is the kernel here, the dot. Actually, I will execute the kernel. Again, I will copy the make file from section 201 to make. We'll see this. Okay, this one has a stat. That's good. Okay, it's running and run. So if I do cat slurm, it's correct. And if I do cat result stats CSV, the kernel takes this time that this is in Syria. So I will add this performance. Serial time will be this one. The exercise what I will do is I will shift this. No, it's not possible to. Yeah, I will make 3 versions of how many lines is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I need to do. Let's see if that works. Paste. Yeah. And paste. Okay, so I have 3 kernels here. I will call it the dot serial. This will be the dot parallel, and this will be the dot atomic. See if I will have time to atomic. Right, the dot parallel. I need to get rid of this. So I'll fix the indentation. Okay, so here I declare this have the thread ID, the result sum, and I will create a shared vector that will be called TMP, and the elements that I will need will be a thread per block. Oops. Because remember that this variable is I forgot what this will be double. Remember that the shared memory is shared within the block. So makes sense that the size will be the threads that are inside that block, because each block will have their own shared memory. Okay, so these are the variables that I have, and what I need next, I need to do the calculation in parallel. So let's do that. A second. The calculation in parallel will be here what I'm calculating will be TMP will be thread idx.x equal x tid multiplied by y tid. So here in this temporary array, I'm calculating these values here. And here, remember, once that I finish that, I will need to synchronize, I think it was sync threads. I will need to synchronize the threads, because here, at this point, I will what I will do is I will do the addition of all of these elements that are in this temporary array and update result. So there are like 3 steps. Let's say step 1. So in threads, step 2 is let's say local reduction. Also, I will this local reduction will be done by I think TID or thread ID should I use? Okay, that makes oops. If I use this will be only calculated by one thread of the whole kernel. So here, this is not recommended. I should use a thread idx.x equals 0, because this will be calculated, in that case, the thread 0 of each block will calculate the local reduction. Some 0 here, because the multiplication is already done. I will do TMP I en is not n should be threads per block. this is done. And here the step 3. The atomic sound. So here, rather than using this, I will do atomic add, and I think was result some. Let me check the syntax if that's the right one. Yeah, it is the right one. But they realized here that they made a mistake because this atomic addition will be done by every thread that is on this. So I will need to include the step 3 after the. Let me see how can I copy this. And the step 2 will be here. See if that works. No. Sorry, it's a bit of a mess. I'm using a VI, and maybe that's not the best, but here I need to get rid of this. Okay, so this should be the kernel. Just to recap, well, this is the declaration of variables. Here I calculate the partial multiplications. Actually, I'm spotting here something that I don't. Yeah, this is not. There is some mistake here. We need to double check that this is less than, and also will initialize the variable TMP. Oops. Yeah. So we do the partial multiplication here, sync thread, and then the main, or well, the thread 0 of the block will do the local reduction, and we'll add the atomic add with the. So in this case, the number of atomic additions will be reduced. Okay, the last thing that I have to change and copy, where is the, here, the dot touch parallel. Let's see if that compiles. Oops, yeah, and slash submit. It's running, finish, Let's see if the result is okay. No, I want to see slurm. 5, yeah, that one. Okay, the result is correct. And the cat results stats.csv. The performance takes this. So you see that this is the yeah, in parallel is quite fast. I have 4 minutes to do the third version. The third version is only using atomic operations. So will be the dot atomic. So in doing this, what I do is, I think I don't need this. Let's fix the conditional. Right, okay. So the for loop, I do the yeah, I don't need that either. So what I need is atomic add result x. No, actually, this xtid multiplied by y tid. I need if tid is less than n. So this will be the I think this will be the equivalent of actually, and also I don't need this variable. Oops. I'm pretty sure that should be something like that. You see that it's pretty simple, but performance might not be the best. And result, I think, yeah, okay, initializing the. Let's try. I not sure if that will work, but let's. Oops, okay, I forgot to change this because I want to call the dot atomic. Well, make. But submit. Yeah, done. Katzler. The last one is 6565. No. I see. Yeah, the result is correct. And let's see the performance. Stats. Oh, yeah, performance doesn't look quite good. Let's see. Oops. Okay, that's quite. So you see here the performance of the elapsed time is even longer than the serial. Why? Because the problem is that for each position of the vector, we lock the variable, do the operation, and unlock the variable. That serialize the execution, and also there is a lot of overhead of locking the variable. I don't know how long the vector is, but that number of times and locking, this is a lot of overhead. So you can see that we should be careful using atomic and reduce the number of uses of. You may think that the parallel version is quite complicated because do a lot of steps, use the shared memory, etc. But the efficiency is better. Not sure if you have any questions. If not, we are now in the break time, so we will have a break until 11. I will stop sharing. No, I wanted to share this. So yeah, we are now on the morning break. At 11, we will see streams, and later, yeah, we will have like some time for exercises and questions until noon. Okay, so yeah, see you at 11. In case that you have any questions or anything, please let me know. I'll probably be around. Okay, welcome back. Let's share slides. Make this here. Right, so now we will talk a little bit about streams. So far, what we have seen is we have used only one stream. Stream are the operations that we do on the GPU. We have done a normally memory copy from host to device. We execute the kernel. We copy back from device to host. No, that's it. But we will see that we can use more than one stream. We can use one stream to the memory operations, one stream for the kernel, or we can use several streams for different kernels. We can see that we can use more than one stream. Using several streams, we can also overlap operations. So we will have the let's see the parallelization that the GPU provides, but also we will have a concurrency. So this is useful when we have several GPUs. One stream could be a GPU. So while also we can use streams to run more than one kernel at the same time. Why streams? We can use them to overlap data transfers and computation to execute several kernels on the concurrently to do asynchronous memory operations or for pipeline processing. There are like a different scenarios where we will benefit from using more than one stream. Also are useful for load balancing and real-time data processing, or as I said before, multi-GPU systems. You can have one stream per GPU and work concurrently using several GPUs. This is a new syntax. So to declare a stream, we can do, well, yeah, the type will be a heap string underscore t. We will need to initialize the stream with the heap stream create. And when we don't longer need the stream, we can destroy it. We can free or release that stream with the heap stream destroy. We have seen so far synchronous copies of heap main CPI, main copy. With the streams, we can use the asynchronous version of a main copy. In that one, we can specify the stream at the end of as an argument at the end of the function. If the function, if that argument is not specified, it will be the default stream that I think is the number 0, if I remember right. Well, this is a note saying that heap memory asynchronous, yeah, it still use both host and device memory references like a heap main copy. To synchronize, because when we, for instance, for the memory copy, if it's asynchronous, we don't know when the copy has been done. So to be sure that the memory copy has been done, we will need to use heap string synchronize. And this is a blocking function operation. This function will block until all depending operations in the stream has finished. We can also select the when we submit a kernel. Remember that we were specifying the number of blocks, the number of the threads per block, the size. Also, we can specify the stream. And you have seen last week that we can submit the kernel either using this syntax or using a heap launch kernel GEL that has this syntax. Here we were talking, there is another concept that could be useful to know at this stage, that is about pin memory. Pin memory is, we were talking yesterday about the page faults, that a memory could not be available on memory and for some reason could be on swapped to disk. We can use well, the function heap host malloc to allocate pin memory. Pin memory means that that memory will be always on RAM, will be always on memory, will not be swapped to disk. So if in case that you want to use that memory, or that, let's say that the memory that you use to give that property of ping or page lock, you will need to use a heap host malloc. And remember, to free that memory, rather than to use a heap free, you will need to use a heap host free. The benefits of using that, there could be a faster data transfer between the host and the device, because the memory will be always on memory, will not be on disk. The performance is more predictable because, yeah, they will could depend on the execution, that if the memory, in some executions, if the memory is on disk and the memory is on let's see, the data, in same memory, but it's the data. If the data is on disk or the data is on RAM, could vary the performance, but if the data is all the time on RAM, the performance will be similar between executions. And also, it's more efficient to have access from the GPU to that memory without using the GPU. It doesn't mean that they have you will still need to do data transfers, but will be the more efficient. Also, yeah, it's good to know that PIM memory is like not as available as the memory that could be that could be swapped to disk, that is called here pageable. So please, because the PIM memory is like more efficient, don't use it, because could be cases that you have some images or some pictures or some matrices that are quite big, and maybe they don't fit in PIM memory. So be careful when you use data memory. Right, so we have this exercise here, that what we will do is for this exercise there is a template, and we have the vectors x and y that we will need to do a memory copy. So rather than doing a synchronous memory copy, we will do an asynchronous memory copy. We will create two streams. One stream will copy the vector x, and the other stream will copy the vector y. Also, be careful or make sure that the data is on the device before launching the kernel. For that, you will need to do a stream, synchronize the stream. Said here before, this is more to to understand the concept. You will not see a huge increment in performance. You can use this tool, Perfetto, to see that you have two streams working on parallel. That might make sense. I don't know if vectors x and y are huge, or you are copying several images in parallel, maybe, but yeah, this is just to play on the concept. So you can replace the logs. Yeah, also you can play on the host allocations of x and y. You can use a heap host malloc, And also, when you free the resources, use heap host free. And with that, please play around and see if there are any difference on performance. So yeah, this is like the, let's see, last part of today's theory. The rest of the time until noon will be to play with this exercise. So if you have any questions or anything, I'll be around until noon.